All right, welcome to the Explainer. Today, we're going to break down one of the most fundamental, and I think one of the most elegant equations in all of science. We're talking about the ideal gas law.
But, before we jump straight into the math, I want to start with a simple, real-world puzzle, just something to get us thinking.
I mean, you've probably seen this exact warning on an aerosol can or something similar, right? And let me tell you, that warning is not just a friendly suggestion. It's a perfect example of a physical law at work, showing how temperature and pressure are directly tied together.
And you know what? This whole thing isn't just some random fluke. It's actually super predictable. And the tool we use for that prediction? Well, that's exactly what we're here to talk about today, the ideal gas law.
All right, so let's talk about this perfect gas equation. It's time to dive into this incredibly powerful formula that, basically describes the behavior of all kinds of gases. So here it is, PV equals nRT. This version of the law was first pieced together by a guy named Benoit Paul Émile Clapeyron way back in 1834. And what he did was pretty brilliant, actually. He took a bunch of earlier discoveries, you might have heard of Boyle's law or Charles's law, and he rolled them all into this one single, super useful equation.
Okay, so to really get a handle on this law, we've got to get to know its components, right? So let's break it down letter by letter.
First up, P for pressure. Just imagine countless tiny gas molecules zipping around and constantly smashing into the walls of their container. That's pressure. The more they hit and the harder they hit, the higher the pressure goes. Next, we've got V for volume. This one's pretty straightforward. It's just the amount of space the gas is taking up. So for our propane tank, it's the inside of the tank. And we're assuming that volume stays the same because, the tank is rigid. Gases will always expand to fill whatever container you put them in.
Okay, then there's N, which stands for the amount of substance. Now this is a big one. It's measured in moles, and basically N just tells us how much stuff, how many actual gas particles we're dealing with. It's a way to count molecules, but on a totally massive scale.
And T is for temperature. Now it's really important to remember this is the absolute temperature measured in Kelvin. In physics, temperature is all about the average kinetic energy of the particles. So put simply, hotter means the molecules are moving around way faster and hitting things with a lot more energy. Last but not least, we have R, the universal gas constant. So what is this thing? Well, you can think of it as the magic number. It's the constant that ties everything else together and makes all the math work, connecting energy, temperature, and the amount of gas in this really beautiful relationship. So let's take a closer look at why it's called ideal. We've been throwing that word around, but why is this the law for an ideal gas, and what does that even mean in the first place?
Well, this classic experiment gives us a massive clue. Here's the setup. You have a gas on one side of a container and a total vacuum on the other. You remove the partition, and the gas just expands to fill the whole thing. For an ideal gas, something amazing happens. Its temperature doesn't change at all. And that tells us something really profound about what's going on inside.
And this right here illustrates the core assumption we're making. For an ideal gas, we assume that all of its internal energy is just the kinetic energy of its molecules, how fast they're moving. We basically pretend that any potential energy from forces between the molecules is zero. In other words, in our perfect little model, the particles don't attract or repel each other at all. So if we compare an ideal gas to a real gas, you can really see the difference. In our ideal model, we assume the particles are just these tiny little points that have no volume. We also assume there are no attractive forces between them. Real gases, of course, are a bit messier. Their particles do have a tiny bit of volume, and they definitely attract and repel each other. But here's the thing. This simplification is exactly what makes the ideal gas law so powerful and so incredibly easy to use.
Okay, so now we know the theory, we know the assumptions, so let's see the law in action. How is this thing actually applied out there in the real world?
One of the coolest things about the ideal gas law is how it simplifies to describe specific situations. So for example, if you hold the temperature constant, you get what's called an isothermal process. Or if you keep the volume constant, that's an isochoric process. Each of these special cases gives us an even simpler relationship to work with.
And we can even visualize all of this on a graph, like this pressure-volume diagram. You can see how different processes follow different paths. See those curved lines? Those represent paths where the temperature stays constant. It's kind of like a map, Changing the conditions moves the gas along these different routes.
So with all that in mind, which one of these processes describes our pressurized propane tank on a hot day? Let's bring it all back to that first question and finally solve this mystery.
It's an isochoric process, constant volume. Think about it. The propane tank is a rigid, sealed container, right? So its volume, V, isn't changing. And the amount of gas inside, N, isn't changing either. So in our big equation, PV equals nRT, if V, N, and R are all constant, then what happens when the temperature, T, goes up? Well, for that equation to stay balanced, the pressure P has to rise right along with it. It's the law.
Okay, so we've seen how useful this law is. But we've got to talk about going beyond the ideal world. It's an incredibly powerful tool for sure, but it's so important to remember that it is just that, an approximation. Let's take a quick look at its limits.
This quote really hits the nail on the head, and it makes perfect sense, right? At low pressures, the molecules are so far apart that their own size and attractions barely matter. And at high temperatures, they're moving so fast that their kinetic energy just completely overpowers any weak attraction between them.
So, the bottom line is that real gases start to deviate from this ideal behavior because, well, their molecules do have size, and they do exert forces on each other. So while the law gives us this fantastic, simple tool for making predictions, it's not the whole story. Especially when you get to really high pressures or really low temperatures, that's when things start to get a little different from our perfect model.
And that leaves us with a really interesting question, doesn't it? These ideal models, they give us incredible predictive power. But how do scientists bridge that gap between the ideal world and the real world? And really, that's the constant challenge in all of science and engineering. The ideal gas law is this beautiful foundational concept. It's the starting point. But the real work is in refining these perfect models to better describe our wonderfully messy, complicated, and very, very real world.